experts near and far. This evening, we particularly welcome as speaker our friend and one-time president and now life member of GAS, Dr. Paul Daniels. He's going to give us an insight into the impact of mega constellations of communication satellites such as Starlink on astronomy professional and amateur. Paul gained his BSc in astrophysics from Queen Mary College London in 1978, where he had also been first the secretary and then the chairman of the Student Astrophysics Society, introducing such luminaries as Professor Ken Bounds, Professor Sir Herman Bondi, and Professor Dame Jocelyn Bell Burnell when she was just a postdoctoral student. He then went on to Sheffield University and gained his PhD on the topic of particle accretion and the size distribution and evolution of cometary nuclei in 1981. Whilst there, he gave adult education classes in astronomy and became the first ever Sheffield postgraduate student to prepare and give and set marks and exam questions for an undergraduate degree course in astronomy. After a year working on image processing software for the ROSAT X-ray astronomy satellite at the Max Planck Institute für Extraterrestrische Physik in Garching, which is near Munich, he returned to the UK to UWIST in Cardiff, left astronomy for a while, and worked on the application of image processing in an industrial environment. Whilst there, he also taught MSc courses in image processing and in the Pascal computer language. After that, Paul moved into computing in the commercial world and in 1988 became a freelance contractor until his retirement a couple of years ago. Around 2000, Paul joined GAS and was soon press-ganged onto the GAS committee. After serving for a couple of years as the GAS webmaster, he then became president for the 6 years between 2012 and 2018 and is now an honorary life member. During his time as GAS president, he joined the Council of the Federation of Astronomical Societies and has been the FAS president for the past 3.5 years. He also rejoined the Royal Astronomical Society as a fellow, was elected to RAS Council in 2016 and elected as one of the vice presidents of RAS in 2019 and is running for election again as a RAS Council member. Results are due next Friday at the RAS AGM. He serves on various RAS committees, including the Megaconstellation Working Group, brackets optical subgroup, which has led him to the topic of tonight's talk. He now lives in Bradenham, near Dereham, in Big Skies, Norfolk, where the nearest street lights are about 2 miles away. Paul, the floor is yours.
Thanks very much. Let's just get my presentation up and going. Can everyone see that? Yes? Can you see that?
Yes.
Okay, lovely. Okay, so this talk, or this introduction that I had to the mega constellation threat began really in January last year, January the 31st. I was invited to a meeting at the Royal Astronomical Society, organised by Robert Massey, where he was inviting a group of professional astronomers together, and I expressed an interest and was included. Now, this meeting was on the 31st of January, and I have to say, when the details came out, I was both shocked and annoyed and surprised and sad about this threat that's going to happen, because make no mistake, this is potentially an existential threat to much of ground-based astronomy and also some astronomy from low Earth orbit. So first of all, where are we going with this? The talk's about mega constellations, so I want to say just a little bit about what they are and vaguely what defines a mega constellation. I'm going to talk a little bit about their threat to astronomy, and then lead on to things such as the safe and sustainable use of space and space debris and so on, which is in the news quite a lot now, and the implications it may have for our continued access to space when you think about launch windows and things like that. There are some legal challenges to megaconstellations, and I'm also concerned about some of the potential international tensions that may be raised by the number of different space operators that wish to crowd low Earth orbit with thousands and thousands of satellites. So it all started back in October 1957 with Sputnik 1. And if you haven't heard John Axtell's excellent talk on Sputnik 1, I suggest you ask him to give the talk again. And Sputnik 1, first satellite, and there have been, and just qualify this talk was prepared back autumn last year. I haven't updated it, so there will be a massive update coming. So this is really the numbers that I give are really numbers that were sort of accurate back then. 8,000 so launches since then, with about 1,950 active satellites at present. Of course, Elon Musk's SpaceX has been launching them at a great rate, and there are over 1,400 Starlink satellites now in addition to that 1,950 active satellites. Now, the thing about satellites was that back in the early days, when the initial novelty of the little Sputniks had worn off, was that you wanted to put satellites up there that had a much more practical purpose. And so typical big satellite used for communications, for television signals, for telephone and computer links and so on, was typically a 6,000 to 8,000 kilogram satellite. That's a big monster of a satellite. And they would cost $100 to $400 million. And the cost of launching them was phenomenal, because a satellite that large takes a lot of booster to get it up into orbit. And also back in those days, you were dealing with satellites that were placed out at a considerable distance, 36,000 kilometers or so from the Earth's surface, where there was a great deal of the Earth's surface visible to the satellite. And you only had a few of them in orbit at that sort of distance. Things have changed a lot since then. The satellites have now come down incredibly in size with the miniaturization of electronics and the reuse of boosters. It's just a technology. The space launch business has become a very mature business, and satellite building has become a very mature industry. So these satellites now, some of the small CubeSats can be launched for $20,000 to $50,000. Usually now, of course, because they're smaller, launched along with several other satellites at the same time. In fact, SpaceX recently set a record with a single launch of 143 satellites at the same time of different types in one launcher. So the fact that satellites have now come down so much in cost means that you can launch a lot of them, which is what's led to the idea of the mega constellation. So where before I move on to that, what do we consider a mega constellation to be? We've all known about the GPS satellites for some time, the constellation of GPS satellites. I don't know how many of those there are, but it's in the few tens of. We have some small constellations, that sort of order, but we also have some maybe that go up to 100 or so satellites, with a constellation really being a system of satellites that work in conjunction with each other. Maybe they're bouncing information between themselves, or maybe they're carefully spaced out to give the sort of global coverage you want. But for mega constellations, we're talking about thousands of satellites, several hundred, maybe up to thousands or tens of thousands of satellites. So we're talking about a much, much larger system of multiple satellites. So I want to talk a little bit, first of all, about the kind of orbits that satellites are placed into. So we start out here with the high Earth orbit. And there aren't many of those. These are satellites placed at an altitude of more than 35,786 kilometers. And I'll explain why that's a magic number in a minute. And when I talk here about altitude, I'm talking here about the distance above the mean Earth's surface, not the distance from the center of the Earth. So this is altitude and not distance from the center. There aren't many satellites out at that sort of distance. They orbit more slowly than the Earth rotates, and mostly I would imagine they're scientific, or maybe they're surveillance satellites or something like that. Not many. Much more common are the geostationary and geosynchronous Earth orbits. The difference between geostationary and geosynchronous is, well, they're both geosynchronous, but geostationary is a special case. Geosynchronous just means that the orbital period is 24 hours, so that the satellite, if the orbit of that satellite is circular, so that its rate of orbit around the Earth is fixed, then it means that the satellite will always stay above the same longitude. And if it's in an equatorial orbit, then it means that the satellite will stay in the same position in the sky. That's the geostationary satellite. Geosynchronous means it's got a 24-hour period. So your sky dish doesn't have to track satellites across the sky, because your sky satellite is at a particular position in a geostationary orbit. If the orbit is slightly inclined to the equator, then the overall effect is that the satellite will move up and down above and below the equator, as the tilted orbit means it goes up and then down below the equator. And if the orbit isn't perfectly circular, then you'll actually have a slight elongated figure of 8, as the satellite sometimes gets ahead of the Earth and sometimes a little bit behind it in its rotation. But either way, it still counts as a geosynchronous orbit. And there are quite a lot of satellites there. They tend to be the big ones, the communication satellites for the older internet ones, the television, and so on. There are some in medium Earth orbit, where particularly at an altitude where they have a 12-hour period, so that the satellite goes around twice every day. And one particular version of that that's quite common is the Molniya orbit, which I've got down here. You can see that it's in a highly inclined orbit. It's inclined at 63 degrees. Looking for my notes here. Yeah, 63.4 degrees to the equator, and it's got a 12-hour period. And the idea of it is that the satellite whips around the bottom very quickly down here, and then it spends a lot more time up here near apogee, furthest distance from the Earth, traveling more slowly, which gives it a lot more time to look down on a continent of interest in the Northern Hemisphere, mentioning no names. And that means that the satellite then has the surveillance job over that sort of continental area. Then it whips around the bottom. 12 hours later, it's up here again, and it's looking at a different continent, or a different half of a big continent. And then another revolution later, it's back doing the same thing again. So this satellite orbit configuration is particularly used for surveillance. And the reason for the 63.4 degree tilt is that at that particular tilt, it turns out that the precession, there is no precession. The satellite stays oriented in the same way all the time. Precession is when the satellite's orbit rotates around an axis which is the same as the Earth's axis. So a bit like I don't know, if you span a hubcap on the ground, you would get a similar sort of effect of rotation. And then you've also got here the ones which are the subject mostly of tonight's talk, which are the low Earth orbits or near Earth orbits. They both mean much the same thing. I've mostly seen LEO as more common than NEO. There's also VLEO, which is very low Earth orbit. And this is typically any altitude less than 2,000 kilometers. And there are, it says here, 1,468 active satellites, but to that, you can now add the 1,400 plus satellites, Starlink satellites that SpaceX has launched. Now, these satellites typically have a configuration of this sort of approach. This is not a single orbit. This is this sort of basket weave of orbits down here is actually several orbits which have the same inclination, but they're staggered in the point where they cross the equator, so that you've got this sort of, this is one orbit, this is another one, this is another one, and so on. So there are a lot of different orbits there staggered, and that's what's called a Walker configuration. And it may be, in fact, that you've got more than one satellite in each of those orbits. And in fact, Starlink do that. They may have as many as 50 odd satellites in some of those orbits. So this is the one that is most commonly being used now for the mega constellations, and certainly it's the one that Starlink are using. So just as a sort of a list of some of the mega constellations that are coming up, we've got SpaceX here as the big one. Well, I'll talk more about SpaceX later, because most of this talk is going to be about SpaceX's Starlink satellites. They happen to be the first ones to get there, and they've got the most in orbit, and so the problems that are coming from them are problems that we may well see from all the others later. I think it's unlikely that any of the others will solve the problems that SpaceX are also failing to address. So we're talking here from SpaceX's satellites, as you can see, potentially a very large number of planned satellites. Not all of these they've got approval for yet, but this is their aspiration. You can see that these are all going to be in a relatively low Earth orbit, whereas some of the others further down currently are being set for targeted for higher orbits. And I'll explain later why it is that the lower Earth orbits, the lower altitudes, are better. So we can see here large numbers of satellites forming constellations. OneWeb down here, when I first started working on this, we had the early days of OneWeb, they actually went bankrupt, and they declared Chapter 11 bankruptcy in the US, which means that instead of breaking the company up completely and disposing of the assets to the creditors, they actually get protection, and they are allowed to reorganize the management. And once they've reorganized their management to the satisfaction of the authorities, they're allowed to open up again and keep going. Basically it's a way of giving a company a second chance to pick itself up and carry on. And they did that. They managed to find some people prepared to buy a OneWeb. This is a company that are going for a slightly different approach to SpaceX. SpaceX are launching their Starlink satellites as internet satellites, with connection down to end user terminals on the ground, whereas OneWeb are looking much more to provide a service to telecoms companies like BT and EE and so on. So they don't need as many satellites. And interestingly, while they were bankrupt, they put in a request to launch 47,844 satellites, which is a pretty bold move for a company that's in Chapter 11 bankruptcy. And I suspect, if I were being cynical, that it's just to make them look more expensive, so that when they got bought out by somebody, there would be more money in the pot to do things with. And they got bought out by Bharti International, which is an Indian company, and the UK government. So the UK government has roughly half or nearly half stake in OneWeb. So you can see here that even if you discount some of the speculative figures here for Facebook and OneWeb down here, because they haven't been given permission for those, they only applied for it, and some of the others, and Link is another one. I've lost Link. Yes, down here, thousands, they don't know how many. If you discount those, the ones that we do know the numbers for comes up to nearly 60,000 satellites. Now, since then, the European Space Agency have said that they would like to look at having a European mega constellation along the lines of Starlink. And the Chinese have also got at least one very large network that they're thinking about, that is going to be up around the 30 or 40,000 satellite mark. So you can see straight away this number of 1,950 active satellites within the next decade, maybe next 15 years, is going to be up nearer 100 and something thousand satellites, with potentially a lot of problems, which is the subject of this talk. So coming back to Starlink, and as I say, now I'm going to talk pretty much only about Starlink. If you want to put satellites into orbit, you want to operate them, you have to get permission from the ITU. Now, the ITU is the International Telecommunications Union, which is actually one of the oldest world organizations. It was some French-named postal and communications union or something under the United Nations, and it was renamed as ITU. ITU effectively, they maintain the register of frequencies that satellites are going to use for uploading information to the satellite, for commanding it, for example, or download when that satellite sends information back down to the ground. And if you're going to operate your satellite, you obviously want to talk to it or get information from it, and you have to get permission from the ITU. Now, the ITU doesn't deal individually with each of the countries. Each country has its own organization. So in America, for example, it's the Federal Communications Commission, the FCC. In the UK, I suppose it would be Ofcom. And similarly, there are organizations in other countries. And so what happens is that the FCC allocate frequency bands on behalf of the ITU, and Ofcom in the UK would do it on behalf of ITU. So the fact that the FCC is in that position of being able to control what frequencies are allocated to you means that you have to go through them. If you're going to launch something from the United States, then you have to go through them as the licensing body. Now, it used to be that you had to have a satellite up in orbit and using the frequencies allocated to it within a certain period of time. And I forget what that was. I think it was 6 years or something like that. They realized, however, that that was rather a difficult thing to do if you were launching thousands of satellites. You'd make one application to launch, say, 2,000 satellites. And well, if you're going to take a long time to launch 2,000 satellites, you may run out of time by the time you've got the last one up there. So is it when you launch the first one and have it working, or when all of them are up there and you have it working? So they came up with a slightly different rule of thumb, which was that you have to have half of your planned fleet of satellites in orbit within 6 years, and the remainder fully deployed in 9 years to satisfy the terms of their allocation of that frequency spectrum to your satellite. If you don't meet those deadlines, then they are fully entitled to return that allocation back to the pool of allocatable frequencies and potentially give them to someone else. And obviously, you know, people therefore have a certain time limit to get the satellites up on time. Now, Starlinks have got to be up there, and I've nominally numbered them here as phase 1, 2, and 3. That's my numbering rather than SpaceX's. They're currently working on launching these first phase 1 satellites into orbit, and they have to have half of them up there by the 29th of March 2024. Now, there are 4,408 of those, and given that there are 1,400 plus that have been launched, they're already well on their way to doing that. They have to have the remainder of them in orbit by the 29th of March 2027, and I would guess that all of them will be up there by the nominal halfway mark rather than only half of them. Phase 2 here are satellites in a slightly different set of orbits, and I think also they're planning to have a slightly different generation of electronics on board. They have to have half of those in place by November 2024 and fully completed by November 2027. So that's the 6 and 9 year period. The application that SpaceX have made to put an additional approximately 30,000 into orbit has been made to the FCC, but hasn't yet been approved. There was quite a hoo-ha made when phases 1 and 2 were announced, and the OneWebs came along, and Amazon's Kuiper project and their few thousand satellites was announced. But I think the FCC have realized that they have to take a bit of a step back in how these launches are, these allocations are managed. So I suspect that there are political delays, meaning that they're going to have to work harder to justify launching another 30,000. Okay, so I did some calculations where if you take a satellite in orbit around the Earth, and you look at how much time the satellite spends above a 1 degree range of latitude, then you effectively, what you're doing is you're thinking of all of the satellites in that orbit being spread out around that orbit. So you get an idea of the density of satellite between a range of latitudes according to a given orbit. Obviously, if there are twice as many satellites in the orbit, then the density is doubled. And up near the top, near the peak of the orbit, near the latitude that's equivalent to its inclination, the satellites there are sort of rising and slowing down before they go back southwards again. And so the density there is also higher. And what this graph here does is to take the numbers that in fact has been updated slightly since my original FAS newsletter article. It takes into account all of the satellite orbits in the blue, the yellow, and the red for phase 1, 2, and 3, so that you can see above each latitude. If you're looking up at the zenith at, say, 52 degrees north, between 52 and 53 degrees north, you can see when the phase 1 satellites have been launched, you can see over here, it's about 0.4, 0.5 of a satellite per 100 square degrees at the zenith. So that gives you an idea of the density. And that doesn't sound like a lot, but just to give you a feel for what 100 square degrees looks like, the square of Pegasus has an area of 207.4 square degrees. So it's about 100 square degrees is about half of the area of the square of Pegasus. The bowl of Ursa Major's dip has got an area of about 43.7 square degrees. And if you count the two quadrangles above and below Orion's belt, then that totals about 81.8 square degrees. So you've got a feel for what 100 square degrees is. It's not actually that large an area of the sky. So that means that if it's approximately 0.4 or 0.5 of a satellite per square degree, if you're at 52 degrees north, so that's what the latitude or just south of Birmingham, latitude of Oxford, something like that, looking straight up at the square of Pegasus, you're almost always going to have one satellite passing through the square of Pegasus at any given time. Now that this is passing through, it's not necessarily visible because it does depend on the illumination of that satellite. So it's whether the satellite's there or not whether you can actually see it. And I'll come on to the geometry for the visibility of the satellites a little bit later on. So you can see that if I were to go back and show you the table again of, which I can do, it's the previous one, you can see here from the inclinations, you can see that there are quite a few at 53 or 53.2 degrees, some higher ones. In fact, these are slightly retrograde. And then there are a whole load of others at 53 degrees in phase 3 being planned, and a whole load here for phase 2 that are planned. So 53 degrees is quite a favored orbital inclination for Starlink satellites. Now, the reason for that, of course, is that the SpaceX motive is first and foremost to give good internet coverage over the United States. There aren't many people who live much north of 53 degrees that make it worth the investment of putting them at a higher inclination of orbit. So, and also not just that, but even if the satellites only go above 53 degrees latitude, excuse me, the satellites can be seen, if you like, further down towards your southern horizon slightly from a few degrees north of that. So in practice, it means that you've really got coverage from large parts of Scotland southwards where you can still see the satellites further down. Plus, some of those satellites are in more highly inclined orbits, but the coverage may not be quite so good. So this particular graph, I will come back to later on. So what do the Starlink satellites look like? This is what they look like when they're all stacked up here inside their launch fairing. There are 60 satellites here. At the moment, they're launching 60 at a time. And they're launched into an orbit of 290 kilometers altitude. And the fairings split apart and the satellites spread out. They come off the launch rails inside the payload. And the satellites then spread out in their orbit. They're all carefully folded up. I think SpaceX have been taking lessons from IKEA. And so that you see they're all in this sort of concertina fashion with the solar panels that then opens out. Now, initially, the satellites will be placed into what SpaceX call the open book configuration. Now, the reason for that is that if you have the satellite in this particular configuration and you orient it so that the satellite is edge on in the direction of its orbit, at 290 kilometers altitude, there is enough atmosphere around to impose drag on the satellite. So if you make the satellite edge on, then it means that there is negligible drag on the satellite. And the reason why you go to this 290 kilometers first is that the satellite at that altitude, you can test it out. You can test that the thrusters work. You can test that the solar panels are working, the comms are all working, and things like that. If it turns out that the satellite is dead, then it will eventually re-enter from 290 kilometers. It will enter back into the Earth's atmosphere in a period of some 14 days or so, depending on what's wrong with the satellite. It may be, for example, that you can command it from the ground, but it's not returning any signals back. And in which case you may be able to command it to rotate flat on, where the drag will be greater and then it will re-enter faster. Once the satellite has been tested, it's then elevated up to its mission altitude. And at the moment, those are around the 550 kilometer altitude. And at 550 kilometers, the satellites there will have they would have about 5 years in orbit if they were uncontrollable, where the drag on them at that altitude is still high enough for them to re-enter in about 5 years' time. And this is one of the big advantages of low Earth orbit, is that satellites that die in orbit will have enough drag on them to cause them to re-enter. Starlink have said that certainly the later generation of Starlink satellites are 100% destroyed in the atmosphere on the way down. When they're actually in use, they move the satellites into this what they call shark fin configuration, where the solar panel is at right angles to the body of the satellite. And also what they've done in the later models, and I'll come back to this later, is they've added down here some little visors to the underside, the leading edge of the satellite. So the idea is that these visors will cast a shadow across the underside of the satellite. And the advantage of that is that that's the aim, is to reduce the brightness of the satellite as seen from the ground. So that's what the satellites look like. But if I just go on to some of the figures about the satellite here, the initial few that were launched, the Starlink 0.9s, and some of those have already re-entered. They were a little bit smaller, a little bit lighter. They only used one of the frequency bands, and they weren't entirely destroyed on re-entry. The later ones here, heavier, used 2 bands, completely destroyed on re-entry. They tried to and make these darker, and this seems to be part of the strategy of SpaceX, is that rather than build the satellites and test them completely in vacuum chambers and dark rooms to test the reflections off them and things like that. They launch them and see what happens. I suppose if you're a multi-billionaire and you're getting military contracts and contracts from NASA and so on, you've got the chance to build and launch quite a lot of these now, of course, increasingly cheap satellites. And if they don't work properly, then never mind. We'll bring them down and we'll tweak them and do something different. So they tried, because there was a problem with the ones that were being launched as them being quite bright in the sky, they tried coating them with a matte black paint, a very special matte black paint that's sort of blacker than soot in appearance. And it was found to reduce the brightness of these satellites by about 0.8 of a magnitude, which is not a huge amount. You're talking about reducing the brightness from, say, 4th magnitude down to 4.8 or something like that. Although some of them are much brighter than that, particularly when they're still spreading out in their orbit, the 290-kilometer orbit. A lot of these are significantly brighter. So this is when they put the VisarSat on. And it says here that the VisarSat trial is still in progress, but now I can tell you that VisarSat is also making only a relatively small difference of about a magnitude or so, such that these satellites are currently, when they're in orbit, when they're actually in their on-station orbit, they are only just fainter than naked eye brightness, which is not really good enough. These satellites all have krypton gas thrusters, which they use to keep the satellites in orbit. Clearly, if you're at 550 kilometers and there is any drag on your satellite, you need actively to maintain your altitude. So that's what the krypton gas is for. It's a very gentle, very low thrust that is used to keep the satellite up in orbit. Also, if it turns out that you have to steer around another satellite, then you can use the krypton gas thrusters to provide a little nudge to the satellite to cause the orbit to change slightly to avoid collisions or something like that. Also, you may use the krypton gas at the end of life. Whatever's left, you'll use some of the gas that's reserved so that you can effectively turn the satellite around and use it to decelerate the satellite and accelerate its inward fall back down into the Earth's atmosphere for re-entry. The underside of the satellite has several antennae, high-speed, beam steerable phased array antennae. What that means effectively is that the satellite is capable of picking out antennae on the ground and communicating with them, with several of them all at the same time. Very, very sophisticated beam pointing ability. There's a single solar panel, 1 by 9 meters. They have a star tracker to help them with pointing. And also the satellites are fed with the United States Department of Defense data, so that if there is a potential collision coming up, they can work on it in advance with enough time to steer the satellite to avoid the collision with other satellites and with other debris. They're starting now to launch the satellites with interlaser communications, so that if you are in Australia and you make a request of a web page in the UK, then your request will get beamed up to a satellite that's passing overhead. It will get bounced around the Earth from satellite to satellite to satellite to satellite, and then the signal will bounce from the satellite over the UK down to the ground station. Now, that means that the delay is significantly less than you would have if you were to send it through optic fiber on the ground. Because if you think about the signal and the time of the speed of light in air and in a vacuum, it's about 1.5 times faster than the speed of light in glass. So optic fiber being made of glass. So it means that the actual time taken for the signal to go up to satellite, around satellites, and down from the satellite down to the UK is a lot less than optic fiber, not counting all of the electronic relays and things in between that used to boost the optical signal that's passing through the optical fiber. So I've seen some measures of around 15 to 20 milliseconds of latency for some of the installations that have already been set up in the United States. And speeds, I've seen speeds reported up to about 220 megabits per second, which is pretty good. The satellites have a fairly small footprint on Earth. A satellite in a geostationary orbit can see about 40% of the Earth's surface, but these satellites down at 550 kilometers can only see about 4% of the Earth's surface, which is the reason why you have to have so many of them, because if you're going to provide coverage, you've got to have a very good chance that there's a large number of them potentially in range of your ground-based antenna looking upwards. So what do you have on the ground? There's this round antenna. It steers itself. It can track the satellites, and it can steer itself to acquire another satellite. It also has steerable beams in the same way that the satellite itself has steerable beams. And initially, Starlink, SpaceX rather, have been sending these out as on a beta basis, what they've called their better than nothing beta promotion. And it costs you $499 to get the initial kit of the antenna and the router, and the initial registration, and thereafter it's $99 a month for the broadband, which for those of us here in the UK in city areas or built-up areas, that's a lot of money. Having said that, when I first moved here to Norfolk, I was paying about £100 a month for my broadband, and it wasn't anything like as fast as the ones that Starlink claim. But for those people in the US, there are large areas of the US where there is literally no broadband coverage from either mobile phone cell masts or from optic fiber or cable or anything like that. And for many of them, this is the only internet that they're going to be able to have for the foreseeable future. So for them, $99 a month is that or nothing, really. The dish is about the size of a large American-sized pizza, and it's been nicknamed Dishy McFlatface. And with this rather odd, futuristic-looking router down here, I haven't quite yet figured out how it stands upright, but I suspect it must have a small flat area underneath. And so, at the moment, it's working well, but there are occasional drops in service because there isn't the coverage that will be there when all of the satellites are in place. So certainly as satellite coverage goes and as satellite service goes, providing broadband, it's certainly a very workable solution. The interesting thing is going to be the economics of it, because it turns out that this satellite dish here currently costs about $1,000 to make. So there's clearly something wrong at $1,000 to make when the initial setup charge is $499. So they're starting this up really working at a loss. I don't know whether it means that the cost will go up, or more likely that the manufacture of these satellite antennae will come down. I suspect the latter. And they've applied for a license. They've applied, because when you apply to the FCC to launch your satellites, you also have to apply for the ground stations. And so they've applied for a license of up to 1 million ground stations in the United States. So they've prepared for this well. So that's the Starlink satellites and what they look like and how many there are going to be and so on. But there are a number of conditions that you also have to satisfy the FCC with. It's not just the ones of the frequencies that you're going to use to talk to the satellite and have it talk back to you. You also have to, for example, make sure that you have collision avoidance. You don't want your satellites colliding with each other. And if you start out with a couple of thousand satellites in orbit, active satellites in orbit, and you come along and say, well, I want to launch another 40,000, you have to really make sure that you convince the FCC that they're not going to collide with each other. You have to remember that things that are in orbit have an incredible amount of kinetic energy. So you have a 1 kilogram CubeSat, which is about 4 inches by 4 inches in cube size, traveling at 7 kilometers per second, which is a typical sort of orbital speed, it's got the equivalent energy of 6 kilograms of TNT. If a CubeSat collided with, for example, the ISS, then it would be catastrophic. It would be a terrible damage wreaked, probably significant loss of life, if not total loss of life on the ISS. So you really have to make sure that you avoid collisions. There have been estimates made by both ESA and NASA, and there's a difference here between, you can see the sort of the Teutonic European size estimates and the NASA estimates here, between 10 centimeters, greater than 10 centimeters, 1 centimeter, 10 centimeters, 1 millimeter, so very quantitative. Whereas you've got here the NASA estimates bigger than a softball, bigger than a marble, or too small to track. But either way, you can see that there is a lot of stuff up there. Some of the very big objects are things like spent rocket boosters that haven't fallen down to Earth yet. Things like spanners that an astronaut has accidentally let go of and couldn't get it back again. Things like perhaps a bag that was let go, or perhaps a component of a satellite or something like that. Bits that have come off, like space fairings that shroud the Starlink satellites when they're being launched. They stay up there for a while. So there's some very big objects up there. If they're large area and thin, so that their mass is fairly small, of course, that means that relatively the drag on them from the atmosphere will bring them down relatively quickly. But the bigger, more dense objects up there will take a lot longer to re-enter. And some of the very small stuff, and I'm talking here about the sort of 1 millimeter to 1 centimeter stuff here, can even be things like flecks of paint, where maybe you've got a rocket booster up there and a micrometeoroid has come in and impacted it, and it's splintered off flecks of paint or little balls of molten metal. And so some of the small stuff that's in orbit around the Earth is down to other impacts. You may, for example, get a very small fleck of paint traveling at 7 kilometers per second, has relatively large amount of energy, and it's quite capable of impacting a satellite and causing little droplets of metal to be evaporated and melted off the surface of the satellite, so that those little droplets of metal are now in orbit around the Earth, as well as the fleck of paint. We really have to make sure that we reduce the amount of orbital debris, and there's a lot in the news now about various attempts to find ways to reduce the amount of orbital debris around Earth. SpaceX have claimed that the satellites will be able to autonomously avoid other satellites. Let's hope that they're right. The other thing is, of course, your satellites, not only must they not collide with others, is that they should not explode. Well, that sounds obvious, really, but of course you've got batteries on board satellites, you've got electronic components on board satellites, and you've even, in the case of Starlink, of course, you've got the krypton gas thruster, you've got compressed gas components on there. And whilst obviously they make great efforts to make sure that none of these components will explode, you shield the gas canisters, for example, you shield the electronics, but even so, as I've already said, given the speeds that debris travel at, it's quite possible that something could puncture that shielding. The battery could fail and could explode. So there's a lot of work that goes into making sure that the components that are in a satellite don't go explode, because if they do, you end up scattering more debris into orbit. So SpaceX had to provide the FCC with their plans to deorbit, so not contributing to the amount of stuff in orbit. They said that a dead Starlink satellite in a 550-kilometer orbit will deorbit solely due to drag within 5 years. NASA, for many years, have had a limit of 25 years on the time taken to deorbit, and I suspect that that's going to be under review. They use the fuel to lower the perigee to less than 300 kilometers, but maintaining the apogee at 550. This takes several weeks. These thrusters that I've talked about are very low power. To get from 290 kilometers, which is the initial injection orbit, up to 550 kilometers takes 43 days to raise the orbit. So it's a very slow spiraling out process rather than a heavy duty powerful burst taking it up into orbit and then another one to decelerate it once it's in orbit. It's a very slow spiraling process, 6 weeks or so. And so it uses this fuel to slowly, this is when it's finished, to use the several weeks to spiral back inwards, but it has to make sure that there is enough fuel there so that as it's coming back in again, it can still maneuver to avoid other objects like the ISS, like other satellites. They also, whereas when they launched, they were deliberately trying to minimize the cross-sectional area of the satellite in the direction of travel. Now they're trying to maximize it. So they turn the satellite literally flat on with the solar panels so that the solar panels are acting like big parachutes effectively. And they will slow it down and cause the rate of re-entry to increase. They spin down the reaction wheels, drain the batteries and power them down. And then within the matter of 6 weeks or a couple of months, the satellite will re-enter the atmosphere and be destroyed. Now, this is all well and good, of course, assuming that you can command the satellite to do what you want. If it's died in orbit out at 550 kilometers, you've now got a dead satellite that's slowly spiraling in over a 5-year period and can't be contacted and can't be controlled. So this all works well, provided you can still command those satellites to do what you want. So let's just think about some of the numbers here. The mission lifetime is about 5 to 7 years for any given satellite. And if SpaceX do get permission to launch the other 30,000, so that they've got 42,000 of them in orbit, and I'm only talking about SpaceX here, but if they don't get permission to launch the other 30,000, you've also got to think about the Chinese and the Russians and everybody else who wants to put them up there. So it may be that these numbers are not so daft, even if they don't get SpaceX don't get the other 30,000 up. But let's just talk about SpaceX alone. And if they do get the 30,000, if you just divide 42,000 satellites in orbit by a 5 to 7 year lifetime, that means between 500 and 700 satellites per month will be deorbiting. 5 to 700 per month. Now that means that you've got 5 to 700 slowly spiraling in over that 6 weeks to 2 month period. And of course, you've got to launch 5 to 700 a month to replace them. So that's a lot of launches, and it's a lot of satellites on the way down, a lot of satellites on the way up, which means that even if you were able to make those satellites fainter at their mission orbit, they will be brighter on the way down and on the way up. You've got the pollution from the launch vehicles and pollution from the re-entry. And think about all those rare earth metals, cobalt and niobium and tantalum and all of those that go into modern day electronics. And the end result of this is that instead of having it back on Earth where you can recycle it, it's being vaporized and scattered all over the Earth and not reclaimable. You've got all of this orbit raising and deorbiting, and even if only half of them are brighter than they are when they're in orbit, you've got about 600 brighter satellites in the sky, not necessarily over the same part of the sky over you, but scattered around the Earth somewhere, there will be another 600 brighter satellites. During the time of the service, when they're actually being used, SpaceX has said that they will try to orient the solar panels for minimum interference with ground-based observations. So that means that they will have to rotate the satellites to try and make sure that there aren't reflections, unnecessary reflections and glinting. But during the actual process of ascending them to orbit, when they're going to be in this edge-on configuration, the open book configuration, the optimum configuration for reducing drag on the way up and the optimum configuration for maximizing drag on the way down may not be optimal for reducing reflections. So even if they do manage to reduce the brightness for when they're actually in surface, they're not going to be reduced in brightness after launch or before re-entry. And also, if you've got something like 600 satellites re-entering the Earth's atmosphere each month, that's 20 a day, then somewhere across the globe, there will be 20 satellite streaks across the sky as a result of re-entry. Excuse me. So you can see the potential problem here. And as I say, this is just SpaceX and their aspiration for 42,000 satellites, not counting the others. Now, you may all have heard of something called the Kessler syndrome. This is the potential for a chain reaction of space debris. And you may remember the film Gravity with George Clooney and, I've forgotten the name now. And they were basically trapped in space when a Russian missile destroyed a defunct satellite, and the fragments that it produced destroyed both a space shuttle and the ISS. And they referred in that to the Kessler syndrome. Okay, the film was fanciful. It doesn't happen quite the way that they've put it, but this is it's named the Kessler syndrome after a chap called Donald J. Kessler, still alive. And in 1978, he and Burton Coeur-Pallet published a paper where they were analyzing the effect of satellites around the Earth if there were collisions. They gained their insight because they did work initially on collisions in the asteroid belt. So they applied all of the dynamics and statistics of asteroids in the asteroid belt and how the asteroid belt grinds itself up with multiple collisions to the process of satellites in orbit around the Earth potentially grinding themselves up because of collisions. And what they did is they came to the conclusion that if the growth of satellites that they were seeing back in 1978 carried on, that there was the risk of a self-perpetuating cascade of collisions by the year 2000. So obviously that hasn't happened. It's a bit like 1984. That prescient book hasn't happened yet, quite. But we have the risk still of satellite debris around the Earth, producing, they suggested, a ring system similar to those around Saturn or Uranus. Now, one of the advantages of low Earth orbit, again, of course, is that even if there were a collision between two satellites and it caused debris, I was in a conversation with Hugh Lewis at Southampton University, and he researches space debris and collisions and things like that. And he said, well, the big advantage, of course, in low Earth orbit, you're going to have the debris re-enter. A large proportion of it will re-enter in time, because you're in a low Earth orbit with atmospheric drag acting on the particles. Now, I think that's reasonable. However, if you have a collision take place and a lot of particles created, some of the fragments will go outwards. And of course, some of the fragments may be large enough that they don't re-enter quite so quickly. And they could potentially lead to another collision. And even if it didn't progress to the point where there was an out-and-out chain reaction causing this catastrophic destruction of all satellites, artificial satellites around the Earth, you may end up at least with a spike in the amount of debris going around the Earth. And so I suspect that any collisions that take place will make use of and access to space significantly more dangerous, not only for things that are already in orbit, but things that maybe you want to launch into orbit or launch through that cloud of particles out and beyond, perhaps to the solar system. Imagine having worked for many, many years on the Cassini spacecraft, only for something to collide with it as it's being launched. I wouldn't want to be on the ISS with a hailstone of debris at 7 kilometers a second orbiting around. So just talk a little bit here about the radio spectrum. This is a diagram of the frequency bands allocated by the FCC on behalf of the ITU for the Starlink project. And you can see here that you've got these red boxes here are 2 commonly used radio astronomy bands that are reserved by the ITU for radio astronomy use. You've got a couple of bands here, space to Earth, and here you've got Earth to space, calling Major Tom. So we've got a downlink, and an uplink. Now you can see here that this particular downlink is quite close to the radio astronomy band. And anyone who's familiar with electronics will know that if you're going to try and design an antenna, it does not just send its beam in one direction. It tries to. You may design it as accurately as you can to send to, but you get side lobes. Also, the electronics, you may try and concentrate the energy of your transmission into one specific frequency, but you get side bands, and it's a natural consequence of the electronics. You try to reduce the side bands because you want all the energy to go into your main frequency, but you can get side bands. So what Starlink or what SpaceX have agreed to do is to ensure that they leave a 250 megahertz wide band between this one here and the radio astronomy band. Now, you have to remember that radio astronomers are looking for all sorts of molecules out there in other galaxies and nebulae and so on, water molecules, OH radicals, cyanide and CO and things like that. And it's all very well and good. I mean, if you could list all of the particular frequencies that you're interested in, then you might think, well, okay, that's great. You can just mark them off and say, right, we'll avoid all of those. But you have to remember, of course, that if you're looking at galaxies, they may be receding from us. They may be redshifted. And so those frequencies that you're looking at may be redshifted away from the reserved band that you're looking at to a part of the band that isn't reserved. So this process of reserving bands for radio astronomy is a little bit, it's not ideal. I mean, it works well maybe within our galaxy, but it doesn't work so well when you're looking at other galaxies, when things are redshifted. So a lot of the ground-based radio telescopes, like the Square Kilometre Array and so on, they have what's known as an RQZ, a radio quiet zone around them of a few miles. And you're not allowed to use a mobile phone within those zones, and so no transmissions, so that the radio astronomy site isn't interfered with that in that sense. So SpaceX have said that they will try to program in to their satellites the ability to steer the beams, the downward beams, away from those sites. Whether that's going to be good or not, I don't know. I don't know whether side lobes might be an issue, where you steer the beam away, but a side lobe is still pointing inwards. But of course, what happens with the smaller radio astronomy sites? If you've got Fred Bloggs in Manchester with his own little antenna in his back garden, they're not going to steer beams away from Fred Bloggs' setup. So we have to find out, we have to determine really how sensitive receivers will be before they start picking up satellites passing through the beam of your radio telescope dish or antenna. The other problem is that these satellites, even if they were to stop deliberately transmitting signals down to the ground completely, no beams down at all, the electronics within the satellites is enough, electronically loud enough, for things like the Square Kilometre Array to detect it. So even the satellites passing over with no downward beams are still a source of interference, admittedly much fainter, but of course you are talking about very large high gain antennae with very high gain receivers attached to them. There was some concern, in fact, as to whether or not something passing over with the beams turned on might actually damage the receivers because of the overload. But I think they've done some work to suggest that that's probably not quite enough to happen. So that's the radio part of it. Now I want to just talk a little bit about the visibility of the satellites. We've got here satellite passing here with the sun 15 degrees below the horizon. And we've got satellites here which may be above the observer. So this diagram is drawn to scale. It's got a satellite in an orbit of 1,000 kilometers. The only thing that's not to scale is that this is one humongously large observatory. But professional astronomers typically reserve their observations for 30 degrees or more above the horizon, so that there's this 120-degree cone here where they do most of their observations. Amateurs, of course, may look further down, and sometimes professional astronomers also look further down, maybe if you're looking for things that are nearer to the sun or something like that. You very gingerly point your telescopes in that direction. You may get some glinting where the track is roughly parallel to the direction of the sunlight. You may get some glinting coming off these satellites here. So these satellites are going to be most visible optically if you're looking towards sunset or towards sunrise. And it may be as well that here, if the sun is only 15 degrees below the horizon, then it means that all of this cone of observation above is illuminated. All of those satellites can be seen. If you come down to the second diagram down here, where the sun is now 30 degrees below the horizon, the satellites in this part of the orbit here are in shadow, and only these here are illuminated by sunlight. So this is part of my comment earlier on, that just because my graph shows the number of satellites above you per 100 square degrees above you, it doesn't mean to say that you'll see them, because it may be that if the sun is far enough below the horizon, that those satellites will be in a shadow. Okay, so this is very much teaching granny to suck eggs here, but this is just showing the extremes of the tropics, north and south. This is the ground observer looking up to the North Pole star, and in the summertime, the sun is on this dotted line somewhere, and so that at midnight it is only, this is set up for the latitude of Birmingham. At midnight, the sun is only 14.1 degrees below the northern horizon. In the wintertime, however, it is down here, it is 60.9 degrees below the northern horizon. So how far the sun is below the horizon depends not only on the time of night, but also on the season. And so you need to take that sort of thing into account here when you look at this graph, where you can see different colors here for 290 kilometer, 340, 550, and 1,100 kilometer altitude orbit. This shows the percentage of satellites illuminated for a given elevation or given depression of the sun. So if you have a satellite at, let's say, 290 kilometers, which is this white line, and we have the sun, which is say 15 degrees below the horizon, then something like 80% of those satellites will still be illuminated. But because this line is relatively steep, it means by the time you get to astronomical twilight here at 18 degrees, only 35% of them are visible. And it doesn't take much longer for the sun to get down to the point where none of the satellites in the sky will be illuminated. However, if you have the satellites up at a higher altitude, up at 1,100 kilometers here, then it really means that some of these satellites, or many of these satellites, will be illuminated for a very large part of the night, depending on the time of year. So this is my comment earlier on, that if you're going to choose where to put the satellite, it's better off that they're in as low an Earth orbit as you can make, and also fitting in with the fact that you've got atmospheric drag on them. And in fact, SpaceX initially were going to put quite a lot of their satellites out at the 1,200 kilometer altitude, and they've now changed the plan and sort of petitioned the FCC to say we'd like to actually put them in a lower Earth orbit. There was also a big meeting of the AAS last year, and one of their recommendations was that all of these Megaconstellation satellites should be less than 650 kilometers altitude to keep them so that they are not visible, or mostly not visible at night time. Of course, OneWeb have already got plans. They've still got plans to put them up at 1,000 or 1,500 kilometers. So OneWeb aren't quite playing ball with that. And even if SpaceX do the decent thing, in quotes, and they do try to mitigate the brightness, and they do try to choose acceptable orbits, etc., etc., there is no guarantee that the Russians or the Chinese or any other operator will choose to go that same route, unless, of course, legislation forces them to. Okay, so I'm getting towards the break here. So that really describes the geometric ability, if you like, and to actually see the satellites and their illumination. If you're going to try and model the brightness of satellites, of course, they've got multifacets. They have a range of albedos across the surface. It depends very much on the cross-section, the sun-satellite observer angle and things like that. And most of these satellites have been estimated at around 4.2 to 5.9 magnitude at their in-mission orbit altitude. The VisarSat has made them perhaps a magnitude less than that. But when they're orbit raising, they've been between first and third magnitude, which is pretty bright. If you're looking near the sun for comets, or you're looking for Mercury or Venus or something like that, then it may well be that you will see satellites that have glinting off the solar panels. SpaceX have used a rather ingenious device on these satellites called a magnetotalker to rotate the satellites. As you can imagine, if they had to continuously rotate the satellites using the thrusters, then the stock of fuel on board would be exhausted fairly quickly, and their lifetime would be a lot shorter. By using a magnetotalker, however, you can rotate the satellites without using fuel. What you effectively got is 3 coils mutually at right angles to each other. So if you like, you've got one coil for the x-axis, one for the y-axis, and one for the z-axis. And if you pass a current through these coils, then you generate a magnetic field. If you remember your schoolboy, schoolgirl physics, then you generate a magnetic field. And that magnetic field reacts against the Earth's magnetic field and provides a twisting force on the satellite. If you're going to have it work any time before a week Sunday, then you've got to pass a lot of current through the magnetotalker. And that's one of the reasons why these solar panels are so big, is because they need to generate the power required to operate the magnetotalker. Okay, so this is my, I'll make this one the last slide before the break. I was going to do something else before the break, but I'm running a little bit later. Okay, so we've got here a table which is slightly cut down from the one that I had in my FAS newsletter article. I've taken out the 1,000 plus kilometer altitudes on here. What this effectively shows is that if you're standing outside and you're looking at a given altitude, a given elevation above the ground, say, let's say 40 degrees up, then if you've got a satellite that's in a 550 kilometer altitude orbit, if you're looking 40 degrees up from the horizon, then the satellite is 812 kilometers away from you. And since we know roughly what size the satellite is, that gives us here a satellite size of about 2.3 arc seconds in diameter. Now, I've gone for 2 cases here. One where the satellite is going to pass directly over your head, going south to north, and the other one, which is where the satellite is passing east to west above your head. So that's what this range of figures is here. So at 550 kilometers altitude, if you see a satellite, sorry, not above your head, this is at the elevation on the left, then you'll see here, this smaller figure here is the speed, the angular speed in arc minutes per second going north to south. And this one is the speed going east to west. I don't mean east to west, north to south in terms of the compass directions. I mean, as you're looking at it, up and down or left to right, perhaps will be better. So you can see here that the speeds are, either way, they are generally fairly similar to each other. So it doesn't matter really which of the two you take. So I use this then to produce this fairly simple formula, where if you have an idea of the density of satellites in the sky, the field of view of your telescope or binoculars, the time of your exposure, and the time it takes for a satellite to pass through that field of view, then you can work out roughly how many satellites you will see pass through that field of view during the time of that exposure, assuming that the satellites are all illuminated. So I've worked out here some rough figures, and this figure here, ROSAT, is the one that that you need to go back to that spiky graph I had on, I think it was my 7th slide, and you get from that, you get the density of satellites in the sky at the zenith per 100 square degrees. So you need to scale that as well to fit in with this formula. And so if you have a pair of 10 by 50 binoculars with, say, an 8 square degree field of view, then you're going to have, in the time of a 10-minute viewing, you will see something like 6 satellites pass through your field of view. So you put your binoculars on a mount, pointing a particular direction, and you'll see 6 satellites in a 10-minute period. With a typical amateur telescope with a 1 degree field of view, you might see 1 satellite or 3/4 of a satellite during a 10-minute period. However, the Vera Rubin telescope, which is still being constructed, it's nearing completion, hasn't seen first light yet. The Vera Rubin telescope is an impressive telescope with a very impressive, highly sensitive detector. And it's one of these wide field camera telescopes, 9.62 square degrees. It will typically, in a 10-minute period, it would see 7 and a bit satellites. Having said that, Vera Rubin only opens its shutters, I think, for 15 seconds, and then there is a short gap, and then another 15 seconds, and then it moves on to another area of the sky and does the same again. So it takes 2 shots of each part of the sky before moving on. They're much shorter, but even so, the probability of a satellite going through that wide angle is still quite high. It's been estimated that when the full Starlink network is up, 40% of the Vera Rubin telescope images will be useless. And a lot of other observatories that are not as badly affected have also said that their work will be severely impacted. Okay, I'm going to stop there for a break. I think you said 5 minutes, Nick, something like that.
Yep.
Okay, if you're not here, say so. Okay, so I'm going to share screen now with something that a piece of software I developed. I just knocked up. I've got to improve it, but it's just an indication. I'm going to share this first. You won't see it yet. I'll just set it up first. And if I do that, good. Okay, come back to this. Okay, can you see that? The Earth hanging in space? Yep, good. Okay. So this is, as I say, this is a piece of software I've knocked up. It uses the 3.js package, graphics package. It's written using JavaScript. It runs in any browser, any modern browser. And it's effectively 3.js is a wrapper to WebGL, so that you can get fancy graphics, 3D graphics in your browser. So what you can see here is the Earth, and this turns on the first two phases, the first 12,000 satellites going around the Earth. So this gives you a general view of how crowded the skies are, the orbits are above Earth with just the first 12,000 satellites. And again, of course, there are the Russians and the Chinese and everybody else queuing up to put thousands and thousands of satellites in orbit, not just the Starlink ones. If I move in, and I'm having to do this all by buttons, I haven't put in a fancy interface here. So I'm zooming in slightly. Now I also haven't made my satellite dots auto size, so I'm going to just take my satellite sizes down a little bit here. Okay, so if you can see that. You can see here that the skies above the UK are fairly crowded. This is running at 8 frames a second, so it's if I make it run at what ought to be a more realistic speed. So that's typically the sort of speed that the satellites will move across the sky, and this, you can see here clearly that this 53-degree inclination I talked about shows this borderline here, where satellites are coming up above through the latitudes, reaching 53 degrees here above Manchester, I would guess, and then heading on their way down again. So we in the UK, because we're close to that 53-degree mark, may well find our skies more cluttered than somebody living down here in the southern end of the Sahara or down near the equator, because the satellites, as they rise up and reach the peak of their orbit before they go down again, they spend a lot of time around that 53-degree latitude. Now, if I just zoom in a bit more right, if I now turn on the 30,000 satellites, this is what you have, and you can see here that just from this that there are several dozen satellites over the UK at any one time. And as I said, even if you were a little further north looking south, you would still be able to see these satellites towards your southern horizon. These satellites further up here are the ones in the higher inclination orbit, and they don't go quite over the pole, again for the same reason that there aren't many people who live at the North Pole or the South Pole, and in any case you would still be able to see some of the satellites at an elevation above the horizon, not necessarily above. So this just gives you an idea of how crowded the skies are going to be. The other thing I'm going to just briefly show you here is that if I zoom in and you look sideways, so here we're at an altitude of 2,200. Let's take my satellites back down, as I say. So you can see these little dots of light. You could well imagine that if you were in a space-based observatory, and if I go a little bit further in and turn sideways again, you can see here, looking sideways, this is now at an altitude of 500 kilometers. So we're not far off. We're only a few kilometers lower than the orbiting altitude of the Hubble Space Telescope. It's not just ground-based astronomy that's at threat. It's also some orbiting observatories, both Hubble and CHEOPS, and there's another one, but there are observatories in low Earth orbit that potentially could be compromised if they're looking sort of tangential to the orbits, to these shells. They're looking through the shell of this fog of satellites. So also the other thing, of course, is one of the advantages of space-based telescopes is that they generally they're up there because you want to do long exposures, as they did with the Hubble Deep Field, for example. and so you've lost that ability to do that if you've got the pollution from all of these satellites. So if I go back to sharing my slides again. So this is, in fact, you can all go and try it if you want to go and look at that that website. It is case sensitive with the MC, has to be a capital MC. I am in the process of updating the orbits, and also I am in the process of moving some of the orbital calculations onto the GPU, where hopefully the frame rate will get rather higher. And maybe if I can make it high enough, I've got enough computation left over to do some fancy things. These slides, incidentally, will be put up on the GAS website, so you can download the whole lot and look at them yourself. I've also, incidentally, while I'm here, if you use the same URL and /moon with a capital M, I've got a moon simulator, so you can simulate phases of the moon and nodding and libration and things like that. So if you're doing demonstrations, you can do a moon simulation. Okay. So who's affected? The professional astronomers. You've got problems with things like the fast transients, the high Z supernovae, things like that. Wide field and all sky surveys, such as the Vera Rubin telescope, large statistical surveys. Following up on the LIGO or Virgo detections. And also, one of the things that the Vera Rubin telescope was planning to do was to keep an eye out for any potentially hazardous near-Earth asteroids or comets coming our way, maybe able to pick them out, because the VRT has this ability to take a snapshot of a part of the sky, and then I think 3-4 days later it comes back to the same area of the sky and does it again. You've got the opportunity to look for things that move, and if you are having some of your images destroyed by satellites passing through the field of view, it rather degrades that facility. This is a simulation, actually, of what you may get with a satellite trail going through the field of view. What we've got here is a track here, but most of the professional sensors that are being used are CCD sensors, incredibly sensitive, but the way that they work means that they are easily saturated by excessively bright lights, and also the internal structure of a CCD means that you often get ghost artifacts. So you've got the main streak here caused by the satellite, and you've got these ghost images here. Not only are the ghost images there physically somewhere else on the CCD, but also some of the sensor pixels may not recover in time for a subsequent picture. So some of this initial streak may even be there visible on the second of the 15-second exposures that the VRT will do. So CCDs are a tremendous problem in terms of their sensitivity to these sudden bright lights passing through them. So they need to be dimmed. We need to dim those satellites, and that's what the dark sat, the dark coating is for. It's what the visor sats are for, but they're not proving really to be faint enough. They need to be dimmer than they are, because if you're talking about dimming them down to 8th or 9th magnitude, that's still quite bright when you're talking about something like the Vera Rubin telescope. If you could dim the satellites to the point where they didn't saturate the pixels, in other words, you can subtract the profile of the brightness across that streak away from the image, you may still be able to recover what's underneath. Either way, you're still having to do some statistical and numerical jiggery-pokery to get at the image, the underlying image. Amateurs, of course, can do things like stacking to get rid of images you don't use, but your telescope time as an amateur is free, it's yours. The telescope time on something like the VRT is rather expensive. Okay, I mentioned the fact that you may have some problems with doing observation from orbital satellites. HST, Cheops WISE, that's the other one. These are satellites orbiting at a relatively low orbit. Here I've got the HST. This green box here, is this one here, blown up, magnified. These are 540 up to 570 kilometer orbits. So these are them in magnification. The HST orbits between the black dotted lines. So potentially, it is at about the same altitude as the lowest of those orbits. But it does mean that if you're here at the bottom end of this green box looking sideways, you're looking out through all of the satellites that could be in those orbits. So HST, I've been told, is already having some of its images spoiled by Starlink satellites. And I was told Martin Barstow at Leicester University said to me that they're expecting to get at least another 5 years out of HST. But it may be that useful life may be cut short by the number of satellites that are going to be in orbit. Cheops and WISE are similar sort of altitudes. So if you get one that's at a 700 kilometer altitude, if it's looking down in a direction that skims above the Earth's surface, it may cut through part of the cloud of satellites. Okay. You don't have to illuminate a satellite to cause a problem. It could be, for example, radios, one issue. This whole question about illumination doesn't apply to radio astronomers because you're worried about the interference being broadcast by these satellites, not whether you can see them visibly or not. You may also, if you're doing things like infrared astronomy, it could be that satellite transitioning from an illuminated part of the sky into a shadowed part of the sky may still glow in the infrared because the satellite has been in the sunlight and it's cooling down, and so there may be some thermal lag as the satellite transitions into the shadowed side. So with amateur astronomy, we've got generally smaller equipments with a smaller field of view, amateurs are also more than likely going to be using CMOS sensors, not necessarily. Some people have got a lot of money and obviously invest in CCD sensors or ways to cool them and that sort of thing. But by and large, a lot of people getting into astronomy will use an ordinary DSLR camera with a CMOS sensor in it. CMOS sensors are generally a lot less likely to be affected by trails because, for one, they're a little bit less sensitive, and secondly, they don't suffer from the same saturation problem that the CCDs do. So there is more of a potential to process out the streaks on individual images. And of course, as I said, also, it's not uncommon for an amateur astronomer to take a lot of pictures and stack them, and you tend to discard the ones that aren't right. And it may be that you could just discard the ones that have got a satellite passing through. There have also been some suggestions that maybe you could subscribe to a service, or subscribe or join up with a service that will tell you what satellites are going to pass over your location at any given time of night, and you may be able to schedule your observing to miss those satellites, something that's perhaps not quite as open to a professional observer who may have booked his telescope time months in advance. And there is the potential, a niche market maybe, to link those predictions of when the satellites will be passing by to a shutter, so that just before the satellite is due to enter your field of view, you close the shutter automatically, and the shutter opens again once the satellite has passed by, so that the satellite trail is never actually visible. You just keep exposing for the duration of your exposure as you would have done before. All you've lost is perhaps a few seconds during the time that the shutter was closed. That obviously requires an internet link up to the database of satellite orbits to get up-to-date data, and obviously requires somebody to develop a vibration-free shutter. But where there's a will, there's a way. I'm sure that could be done. So this was why I was just talking about the software apps being available and also the possibility of a shutter. And again, echoing the same issue here, that for amateur radio observatories, SpaceX is not likely to be very helpful there, although I don't know how the sensitivity of radio astronomical sites for amateurs compares with the beam strength coming down from Starlink satellite. I suspect it's still going to be an issue. And for the public, there is a loss because, well, I was rather annoyed in the early days of the Starlink satellites when they were being launched and they were in relatively low orbits still. You know, you saw this sort of pearl necklace of satellites going across the sky, and a lot of the sort of less sophisticated newspapers and local newspapers and so on seemed to describe these things as a kind of fireworks show in the sky, something spectacular to look at. But it's newspaper articles in the more in the better newspapers that are slowly making it clear that there is the growing problem of space debris. I was involved in an article for Telegraph a few months ago, and in fact, only yesterday, The Independent has a blog running about the Long March rockets being launched by China, and some of my comments have been put in there. But there is a growing awareness of the impending problem of these, but the impending problem they're most concerned with is one of space debris and collisions and access to space, and the sustainability of use of space, rather than the problems for astronomers. Okay, even if they're mitigated to work below naked eye brightness in service, you will still see them on the way up and on the way down, and you will see the re-entries. And the worry here is if the wow factor is taken out of astronomy, is that you may harm the inspiration of potential young scientists. So we need to work extra hard at persuading people to join the science, and despite the pollution of these things in the sky. As I said earlier, there's always two sides to a story. There is a clash of technology where the astronomers have got more sensitive detectors, better telescopes. They are developing new techniques to observe the universe. And at the same time, there is a growing demand for fast internet access around the world, and particularly in remote areas that just do not have any internet access at all. So there's an element, if you read the blogs and look at the websites, there is a strong element of people saying, well, blow everything else, blow the astronomy. I want to be able to get internet access. I want to watch Netflix in my log cabin in the mountains or something like that. And SpaceX will certainly provide that with Starlink. In terms of where the law is and where the legal challenges could be, the original law that's lasted reasonably well, as 1967 was the Outer Space Treaty, later extended, which effectively said that you have to play nice in space, and it was mostly aimed, actually, if you think about the 1967 period, it's only 10 years after Sputnik, but it's back in the Cold War period. And the big worry was that people would be putting up nuclear bombs into orbit. And if war broke out, then you would have bombs dropping on you from orbit. And so a lot of the Outer Space Treaty was designed to prevent the use of space for weapons of mass destruction. That's not to say it hasn't been used for military purposes, because it's been used for surveillance for a long, long time. And now, sadly, there is some talk about putting things like anti-satellite satellites into orbit and things like that. I won't go into the Bogota Declaration, but basically it was a claim by some equatorial countries on slots in the geosynchronous orbit over their territory, saying that If you, the developed world, fill it up with satellites, with communication satellites, then what happens when we, a small nation, have the wherewithal to put our own satellite up there, you will have hogged all the slots. We can't have our presence in space because you've done that. So we want the bit of the geosynchronous orbit which is above the longitudes, the range of longitudes for our country. We want that bit to belong to us. It was 7 countries, and I think the conference was held in Bogota, which is why it's called the Bogota Declaration. But it was completely ignored by all of the spacefaring nations of that time. The Outer Space Treaty also, this is the one 1967, said that effectively space doesn't belong to anyone, nor does the moon belong to anyone. So, for example, it set the principle that if you land on the moon and plant a flag, it doesn't belong to the country that has that flag. So that's a pretty important principle, that astronomical bodies, that celestial bodies, do not belong to any particular country. And then there was the Moon Treaty in 1979, where the United Nations, sort of foreseeing claims that might come about as space became more and more a resource to be exploited, tried to set in place a treaty to say that the celestial orbits and celestial bodies were under the jurisdiction of the United Nations, effectively to put a foot in the door and say, look, no country can use any part of these. We're the ones that will determine the rules and the regulations as to how the moon is used, or if you go to Mars or something like that. Widely ignored, because by that time, by 1979, all of the big countries that were space-faring nations had realized the potential of space as a resource, either for commercial gain or for military benefit. And so nobody signed up to it, neither the European Space Agency representing Europe, or the United States or Russia and so on. Nobody signed up to it. And some small countries did, but not enough to make it a viable treaty. In 2015, Obama signed an act allowing US companies and citizens to own and sell resources from the moon, asteroids and other bodies. So that meant that if an American company went up to the moon and extracted a few tons of surface material, maybe to try and get the helium-3 out of it or something like that, or they went and used something off an asteroid because they want to extract the platinum from it or something like that, it meant that they were allowed to. They didn't own the moon, they didn't own the asteroid, but they did own what they extracted. This was followed up in April last year by Trump, who signed a similar sort of executive order, recognizing that private companies could claim and recover resources in space. But what was a little chilling was the phrase here: outer space is a legally and physically unique domain of human activity, and the United States does not view it as a global commons. A global commons is the phrase used to mean something shared by everyone, not owned by anyone. And for him to declare that the United States did not view space as a global commons is effectively saying, we get there first, it's ours. Not only applying to parts of the lunar surface or asteroids or parts of Martian surface, but also if they occupy large volumes of low Earth orbit with American satellites, then that's tough. We were there first. So this is very much a case of the US companies have got their foot in the door first, whether it's Amazon or SpaceX, whoever, Boeing. You've got the fact that they're saying, we get there first, we have the right to use it, to dominate that. Now, there were some challenges, and they haven't been fully explored yet, but one of them is this thing called NEPA, the National Environmental Protection Act. And there's this law in the States that says that any government agency has to follow NEPA. Any project has to do an environmental impact assessment before it's allowed to go ahead. And there are only a few agencies that are exempt from NEPA. Sadly, the FCC is one of them. They claimed early on that, well, we're launching these things up there into space. They've got no effect here on Earth, have they? So they were managed to get away with not having to do environmental impact assessments. And there are 2 US senators currently challenging that, and there may be a possibility that the FCC will be forced to observe NEPA. That, of course, will put several years, at least 3 or 4 years, into the life cycle of satellites and force a detailed environmental impact assessment on them. And it may be one of the reasons why the FCC is being very wary about just forging ahead and giving the permission to the other 30,000 satellites that SpaceX want to launch. The other one is that there is a US Council on Environmental Quality, and there is a requirement that government institutions in the US keep their policies up to date. Now, the FCC hasn't done that. They haven't revised their policies in 30 years or so. And so it could be argued that by not revising their policies to keep up to date with the arrival of the megaconstellations and effectively using the old criteria and the old policies inappropriately on these very large numbers of satellites, that they've effectively broken the law by not keeping their policies up to date. So that's another potential line of attack. The difficulty is, of course, that, well, SpaceX have already launched 1,400 plus of their satellites. Even if the FCC said, right, stop, they can't easily turn around then and tell Elon Musk, you've got to bring those satellites down again. And the other thing too is that if SpaceX could easily argue that we have a business plan, we wouldn't have started it if it weren't for the fact that we could go ahead and do this. And if you're putting a stop halfway through, we're now commercially unviable. We need you to pay us back all the money. There are all sorts of minefields there if the FCC were forced to try and go back and retrospectively change its permission to launch. SpaceX are already getting military contracts to explore the use of Starlink. They're already, for example, they've already used Starlink to guide aircraft to refueling tankers flying through the sky to help the aircraft link up with the tanker. They've already looked at things like guiding cruise missiles by using Starlink. Because the SpaceX, the Starlink satellites have not only the public channels, they also have some encrypted military channels that have been put in there right from the outset for the military market. And the military clearly are a very powerful lobbying force in American politics. And so if they are already looking at the benefits of Starlink satellites for the military, it makes it much harder to turn this juggernaut that is SpaceX and Starlink around to stop them carrying on the way they have been. And compounding this, back in December 2019, Trump created the US Space Force. The US Space Force is a 4th armed force. It was originally part of the US Air Force, a branch of that, and it's now been split away as a separate armed service. So there are now 4 armed services. A military service that organizes, trains and equips space forces in order to protect the US and allied interests in space. So that means that if, for example, the Russians decided to take pot shots at American satellites, it means that the US Space Force can take retaliatory action. And I fully expect that the Russians and the Chinese and so on will come up with their own space forces in time. It also fits in very much with US military plans. And I'll just very quickly stop here and switch over to another document that was written some years ago. This one. You can see this document here, Vision for 2020. It was written back in 1998, I think it was. And obviously it's a year out of date already. This was produced by the American Air Force, USAF. And it looks rather dated in some ways. Yeah, February 1997, there we are. And even down to the Star Wars style lettering. And you can see just from some of the language that's used in here, the evolution of space, full spectrum dominance, space power is vital to the attainment of joint vision operational concepts, information superiority. There's a very aggressive militaristic approach to the use, to the exploitation of space. And they, even here, they suggest that space systems will be targets. Space superiority is essential. So even back in 1997, they were very well aware that as a resource for the military, space was going to be crucial. And that's certainly the way they're going. And this is what's fed into the creation of the US Space Force. And even here at the end, you see they have got this sort of space-based laser, sort of implying that they could take out targets from space. It looks a little bit more like an advert from Ming the Merciless than the American Air Force. Okay. So I'll go back to my slides again. I've only got a couple to go now. So, as I say, space increasingly being seen as a valuable resource. So, the Americans attempting to dominate the use of space. They already are in the sense of the number of satellites they've got there. And this sort of, the equivalent of a land grab, if you remember the historically the old Oklahoma land grabs, it's almost the Americans are doing the same with space. If they get to dominate and to occupy low Earth orbit to a huge amount, then they're going to make it very difficult for anyone else to come in and to make use of that and remain safe. And of course, it's bad enough when you've got the Americans with SpaceX and Amazon potentially sharing low Earth orbit, but the Americans and the Chinese, or the Americans and the Russians, or the Russians and the Chinese sharing low Earth orbit, you can't guarantee that their communication is going to be good enough. You know, you move your satellite. No, we'll move our satellite. No, you move yours. You know, there could be tit for tat as to who gets out of the way of whom. Clearly, this all has to be done with an international treaty. There needs to be some sort of space traffic control that everyone will abide by. And there needs to be some international agreement on how close the orbits can be or how many satellites you can put in an orbit. But there are no laws at the moment. The fact that there is the growth of megaconstellations means that there are now big discussions going on with UNOOSA, UNOOSA, how you pronounce it. They are a United Nations body, and there is a lot of pressure for an international treaty. The problem is, of course, that again, the same thing could happen as with the Moon Treaty. Will the Americans, the Russians, the Chinese, the big countries, the spacefaring nations, will they sign up to any kind of treaty that potentially restricts what they can do in space, especially as Trump put in his executive order, space, we don't consider space to be a global commons. They're already saying we don't really want to share it. So getting the players to sign up will be difficult. And there are some concerns as well. If you have a company like SpaceX, to what extent are SpaceX capable of controlling their satellites on an order from the US government? Could you have a situation where the US government may say, you must turn off the satellites when they're flying over Iran? We are requiring you to impose a digital sanction on a country by denying them internet access. You may also have issues where some of the regimes, like Iran and China, where they have gone to great lengths to put firewalls around their country so that they constrain very closely what their citizens can see or who their citizens can communicate with. And if you've got Starlink flying overhead, it's going to be very difficult to stop your citizens communicating in the way they want and seeing what they want from the global internet. And it may be that some of the regimes may take unkindly to that and potentially may start to try and find ways of getting these satellites out of orbit. Okay, so that brings my talk to an end. I hope you found it interesting.
Paul, thank you very much indeed. Questions? I know John Axtell has two, so if John would like to present his first and then hold back while others put their questions by chat.
I think I'm unmuted. Excellent
Yes.
talk, Paul. Thank you very much indeed. An awful lot of very interesting information there, and even-handedly expressed, I should say. I think you've answered most of my second question. I don't know if you saw it on chat, the one
Yes,
about interrupter mechanisms and things of that sort. I mean, can that also be done at professional observatories?
I suppose so. Yes, I suppose it could be.
And subtracting the signature.
The mechanisms might need to be bigger, of course. But I suppose on the other hand, on a large telescope, vibrations likely be less of an issue. Wouldn't necessarily. Yeah, I suppose it could be. Yeah.
Okay. The other one was all of this was fairly predictable. Several years ago. I'm thinking of organisations like the IAU. With the benefit of hindsight, do we know why they didn't get their act together and as a professional community to try and put legislation into place ahead of time?
I don't know the answer to that. That has been asked before. There is a grace period whenever anyone submits something to the FCC. There is a period during which people have a chance to object. And I don't know why the world's astronomers didn't see the submission to the FCC, because they are publicly available. And they're boring as hell to read, I have to say, because they're full of, minute details and pages where there's more text in the footnotes on the bottom of the page than there is in the main text on the page, and things like that. Lots of legalese. And so it may just be that it was missed, but unfortunately they missed the window of opportunity to raise objections. Now with some of the later things that SpaceX have been doing, that they're now more on the ball. So some of the changes, for example, are now being objected to, and not always denied anyway. I mean, certainly you've got people like Amazon and Hughes and so on, who want to launch their own Megaconstellations. They're objecting to some of the things that SpaceX want to do. Just as for example, when SpaceX said, we want to bring some of our satellites that were going to be up in the 1,200 kilometer orbit down to 550. OneWeb said, and Amazon said, well, you're just crowding more into low Earth orbit. You're going to make it very difficult for us. This is anti-competitive. Because they have a point. You're making it much harder for anybody else to get into low Earth orbit. Why, I don't know. I did make a comment in an email I sent around to the Megaconstellation group at the RAS. I said that one of the big problems is, having had this meeting back in January last year, I said, you have to remember that you're thinking like academics. You're used to working on a time scale of months, the time it takes to do the research, to publish the papers and things like that. And in that time scale, he will have launched several hundred more satellites. And you have to think about it from the point of view of a maverick entrepreneur wanting to get his foot in the door in space terms. You need to make these objections early and hard. To which the response was, oh, well, but yes, but this is going to happen anyway. There's all sorts of political pressure for it to happen. And if we go in too hard, he'll just stop cooperating with the astronomical community in trying to mitigate the brightness. So that may be one of the reasons why they were fighting shy of being too critical of SpaceX in the early days.
And you've already made the point, of course, that even if companies from democracies like the US or us at least pay heed to the regulations to a certain extent, there's no guarantee that the Chinese would ever dream of doing so.
Do the same. I mean, if you remember the case a few years ago of the Chinese deliberately blowing up one of their satellites and creating thousands of fragments of debris in orbit. Well, you know, I'm not quite sure they'll do that again, but it just shows that they can play fast and loose with what's sensible.
Indeed. The other point was it was Sandra Bullock.
Yes, I spotted that one. Yes, yes, yes. Thank you.
A question from Neil Miller. What about other usage of satellites? What would stop a super rich corporate marketing department approaching SpaceX to launch a close formation of very bright satellites to maintain an artificial asterism? He was imagining looking forward to a Nike tick or the McDonald's arches orbiting the night sky from almost everywhere on the planet.
In principle, I suppose it's possible. You'd have to be able to justify the enormous amount of, you'd have to have a very large marketing budget to launch a constellation of satellites to do that. But I suppose that they're in orbit, so they are configurable. It would be a very low resolution LED type display passing across the sky. I don't know what laws would be there. Well, as far as I can tell, there are no laws currently in place to stop something like that being done, provided they fit the rules of communication and end of life disposal and all that sort of thing.
Other questions? I see none. Paul, thank you for what has been a fascinating, deep, very thorough, and as John suggested, fair and very balanced view of the chaos that is amongst that we are currently amongst. Thank you very much indeed.
Thank you.
Now, just before we have WhatsApp, I would like just to point out that, that the mid-May talk is from Natalie Rees on asymptotic giant branch stars. Then at the beginning of June, we have Raman Prinja from UCL, I think, on outflows from stars. And then in the middle of June, we've got Susan Cartwright, who, if you remember, was unable to join us at the beginning of the year. I think it was February, because she had a problem with her microwave. Anyway, she's going to be talking about supernovae neutrinos,